If you do a Claisen condensation and you create a ring from it, then it's technically called a Dieckmann cyclization. So this happens when you have two esters in one molecule, and the Claisen condensation is intramolecular. It's all happening within one molecule. That's how you create the ring. So let's try to do a couple of these Dieckmann cyclizations. I find it's always useful to try to think, once you think you've mastered something, try to do it intramolecularly. Try to see if you can understand the same molecule, the same reaction happening between different places on the same molecule, especially if it creates rings, because that's harder to keep track of the carbons. Then you know you'll really have mastered it if you can think of it intramolecularly, especially if you're creating rings. So this, I think, is good practice. And this is also something that happens in biological systems. There's a lot of intramolecular reactions there. So I think it's worthwhile to take a second and learn about these, or at least practice for a second, these Dieckmann cyclizations. I'm just going to build on those Claisen condensation reactions that we've drawn so far. So we have two esters. So already we're suspicious, Claisen condensation. But then we're treating it with sodium ethoxide. Notice how the base matches the leaving group. And then followed in a separate step by acid workup. That's the H3O+. So we have the exact recipe for a Claisen condensation. And what we know happens in a Claisen condensation is that the alpha carbon of one of the esters turns into a nucleophile. The base rips off the hydrogen there. That turns into a nucleophile and attacks the electrophilic carbonyl of the other ester and does a nucleophilic acyl substitution. And we've drawn out the mechanism for that in a previous video, the video on the mechanism for the Claisen condensation. For now, we want to draw the product, so we're thinking about this from the perspective of synthesis. But the point is that we're going to be making a bond between this nucleophile and this electrophile. So that obviously looks like a really weird ring. Let's number that and see what type of a ring we should be drawing. So we're going to have 1, 2, 3, 4, 5, 6, 7 carbons in this ring. So we'll redraw. We have the benzene. That really rigid, very stable molecule that shows up in so many molecular messengers, so many messaging like hormones or what have you. And we're going to have a 7-membered ring here. So already we have 4, 5, 6, and 7. So this, and we know that this is 4 and 5, right? So then we can say, okay, 3, 2, 1, 6, and 7. Okay, now that we've drawn the ring, we can think of what else is going to be on it. Well, in carbon number 7, we definitely still have this ester group. So we're going to have a carbon coming off with a double bond and an ethoxy group. But on carbon number 1, when this nucleophile came in, it kicked the electrons up, you got the tetrahedral intermediate, they came back down, and they kick this leaving group off. So you won't have the ethoxy group there anymore. You will, however, have the ketone. And you'll notice that this ketone is on carbon number 1, which is also, you can call the beta carbon. So if I erase these numbers here, and we look at this instead from the perspective of, we know that with a Claisen condensation we should get a beta keto ester. Well, here's our ester. Here's the carbonyl carbon. Next to that is the alpha carbon. What do you know? On the beta carbon we have that ketone. So we do indeed get our beta keto ester. This is a cyclic intramolecular Claisen condensation, also known as a Dieckmann cyclization. Okay, let's try it with B. So here again, we have two esters. They told us that they gave us a base followed in a separate step by an acid workup, sodium ethoxide followed by an acid workup. Notice that the base matches the ethoxy group, the alkoxy group of the esters. And what we know happens here is that the base steals an alpha hydrogen. Those are acidic. So that turns the alpha hydrogen into a nucleophile. And that nucleophile attacks the slightly positive carbon on the in the carbonyl of the other ester. So that's that electrophile there. So that ultimately we end up forming a bond from this nucleophile to that electrophile. Now this is a really rough draft. That looks that doesn't really look like an organic molecule. So let's think about the number of carbons and then redraw this. How many carbons are there going to be in our ring, in this new ring that we're forming? Well, we know this is going to be there. 1, 2, 3, 4, 5. This 5 will attach to that 1. So there's just going to be 5 carbons there. So let's redraw this, but with a 5-membered ring above the benzene. So we'll have benzene, and now a 5-membered ring. Now let's number those. We know that the 2 carbons in benzene are 3 and 4. That means this must be 2 and 1, and this must be 5. On carbon number 1, well, let's do this. We know on carbon number 5 we'll have that ester. So let's draw the carbon there, double bond to oxygen, single bond to OET. So there's our ester. Now on carbon number 1, we will definitely have the carbonyl, but notice that when this nucleophile attacks, it kicks the electrons up, you get the tetrahedral intermediate, then that snaps back down and kicks the leaving group off, so this ethoxy group will not be there anymore when you do that nucleophilic acyl substitution. So we won't draw that in, but we do still have the carbonyl in carbon number 1. Now we can check to make sure that we did this correctly, because if we did, we should have a beta keto ester. We have an ester here, the carbonyl carbon, next to it is the alpha carbon, and then one more is the beta carbon. What do you know? On that beta carbon we do indeed have a ketone. So we created a beta keto ester and a ring by adding 2 ethers together in an intramolecular reaction. Intramolecular Claisen condensation. That is technically called a Dieckmann cyclization. Okay, let's try one more. Here we don't have a ring to begin with, but we can see that our 2 esters are on the same carbon chain. They're in the same molecule, so this is again going to be an intramolecular reaction. This will create a ring. You have 2 esters. They told us that we're treating this with sodium ethoxide, followed in a separate step by hydronium. So we know that's the recipe for a Claisen condensation. And we know that what happens in a Claisen condensation is the alpha hydrogen gets ripped off by the base, the sodium hydroxide, and you form a lone pair with a negative charge here. Now, you might be saying, how do you know which alpha carbon to choose? All of these molecules that they've given us have been symmetrical. So there's a line of symmetry here, there's a line of symmetry here, and in this one there's a line of symmetry down the middle. So that means that the alpha carbons, each of these alpha carbons is the same. You could use either one, you'll end up getting the same product. If they were different, if the molecule weren't symmetrical, you'd get a mess, basically. You'd get both of them, both of the alpha carbons would be turned into nucleophiles, and they would both attack the other carbonyl, and so you'd get a whole bunch of different products. So here, we have this one alpha carbon nucleophile, and we know that that is going to attack the electrophilic carbonyl of the ester. So we're going to sort of form this new bond here. Okay, well that's a very rough draft. But let's think about how many carbons are going to be in this new ring that we form. We're going to have 1, 2, 3, 4, 5, and 6. This carbon number 1 is going to attach to carbon number 6. So we're just going to have 6 carbons. Well, I know what a 6-carbon ring looks like. I've been drawing hexagons since Organic Chemistry 1. So there's our hexagon. We can start numbering wherever we like. So 1, 2, 3, 4, 5, 6. On carbon number 1, we'll have this ester. So carbon, OET, double bond to oxygen. On carbon number 3, we will have 2 methyl groups. And on carbon number 6, we will definitely have the carbonyl. But when this nucleophile, this alpha carbon nucleophile comes in and attacks that, and here let me erase these numbers so this doesn't look as cluttered, attacks that, the pi bond goes up, you get the tetrahedral intermediate, then the lone pairs come back down and they kick off this ethoxy group as the leaving group, so the ethoxy group will not be there anymore. And so this should be our product. Now, we can always check, because we know that whenever you do a Claisen condensation, you should have a beta keto ester. Well, we definitely have the ester, the carbonyl carbon. Next to that is the alpha carbon, and one more is the beta carbon. So in the beta position, you have a ketone, so this is indeed a beta keto ester. This is the product you'd get when you did this intramolecular Claisen condensation, also known as a Dieckmann cyclization.